Good morning, good afternoon, or good evening, depending on where you are located. And welcome to the month of March 2023 AMETEK Solid-State Control webinar. Thank you very much for joining me and taking time out of your day. And today we're going to be discussing testing VRLA batteries, valve-regulated lead-acid batteries, and a few other things. So first thing I always like to do is ask if everybody can hear me okay. So if you can hear me, please type in the chat and let me know, because there's no point in me speaking to myself. So I'll just give everybody a few moments to let me know. Hello, German. Hello, Jimmy, Robin, Tony, Ali, Andrew. Cool. Thank you very much. Okay, so you can hear me. We can move along. My name is Craig Williams. I am the Senior Technical Manager for AMETEK Solid-State Controls. I have 20 years, actually it's more than 20 years now, in the industrial UPS industry. I used to work in the North Sea oil and gas industry, working on UPS systems offshore. I've worked with all major UPS and charger manufacturers, and I've worked with AMETEK Solid-State Controls for the last 6 years. There will be a lag of around about 30 seconds between you hearing my voice and me seeing a question. Basically, we use Webinar Jam as our webinar platform, and what they have to do is they have to process the audio and the video and send it out to Windows platforms, iOS platforms, and Android platforms. So there is a little bit of time that's required to do the processing for that. And it's around 15 to 30 seconds. So, you know, when you hear me speak, it's actually about 15 to 30 seconds after I have talked, but the chat bar updates immediately. So what we always ask is, if you have any questions, please go to and familiarize yourself with the menu on the right-hand side. If you go to chat, there is a chat function and there is a Q&A function. So if you have a question, it's much better that you put it in the Q&A only section. And if you have a chat, then you can just chat in here to each other or to myself in the chat function. So I will try to leave all of the questions until the end. I usually leave about 15 minutes at the end to go through all of the questions that we've had. Now, if I do see something that's pertinent to what I'm saying and I catch it quick enough, I will try and answer that question. But usually I'm paying too much attention to the slides that I don't see the questions come in. Webinar Jam has a panic button. So if for some reason I see people typing in the chat that they can't hear me, or that their screen has frozen or something like that, then I do have the ability to press the panic button. And what it does is it closes this room, it starts a new room, and everybody is invited back in again. And we just start from where we left off. A very popular question is, will the webinar be recorded? Now, so for everybody who has registered for the webinar, you will receive a link to the webinar recorded version of this video. The problem with that version is you can't fast forward, rewind, and move in between parts. It's just like you press play, and it's just like watching the webinar over again. But if you look in the chat bar, you'll see that London has posted a link to our YouTube channel. And what London does is she takes the webinar Jam recording, converts it to an MP4, and then uploads it to our YouTube channel. So within a day, so that's usually by tomorrow afternoon, that video will be available on the YouTube channel, and you can pause, rewind, forward, share, do whatever you want with that YouTube video. So it's much more convenient to wait for that YouTube video to be posted. And the last thing is the webinar should last around 1 hour. I have been trying to reduce the content of each of our webinars so we can stay within the hour, because I do understand that you have lots of things going on in your busy days, and I don't want to take up too much of your time. So let's see how good I do at that today and see if I can stay within the hour. Okay. So today we're going to be discussing the different types of handheld testers for VRLA batteries, how to interpret the values from the testers, which is extremely important because we send so many people out into the field to work on batteries and test them. And in many cases, we're not doing anything with the data. So basically, we'll learn how to interpret the values. The frequency of valve-regulated lead-acid battery maintenance, and understanding. I added a bit on the end called understanding charger current limit, because that was a question that was from one of our previous webinars. So that's what we have planned for today. Okay. So historically, visual inspections are the best method to ascertain the health of a vented lead acid battery. In other words, a wet cell, where you can see the electrolyte inside the battery. Near enough all battery experts agree that you will see plate degradation. You will see the plate start to fail before the cell reaches failure or seriously reduced capacity. So by doing a visual inspection on a regular basis on wet cell batteries where you can see inside the battery, that is the best way to perform your inspections. But then in the last 20 years, VRLA batteries, valve-regulated lead-acid batteries, have really come to the forefront, especially in UPS applications. And you can't see inside a VRLA. They're designed that way. They have a polycarbonate or whatever the plastic is that surrounds the battery. And you cannot see inside. You can't see what's going on with the plates. So many people were trying to find out, how can we see inside the battery with a piece of test equipment? And over the years, many things have been developed. And the main two types of portable devices to try and see inside the battery are as follows. So we have a DC load tester. We're not talking about doing a capacity test. This is a handheld tester, and that the cell corder, the Albert cell corder, is the leader in that market. And then we have AC signal injection, which is what the majority of all the other devices are. Think the Midtronics or the Fluke BT150 tester. Most other battery testers are AC signal injection. And we'll explain the two types and how they do their measurements and how to understand what they are reading. Okay. So first of all, for the Albert cell corder. Now, before I go any further, I am not endorsing any of these tools whatsoever. We have no relationship with any of these tool manufacturers. They are just what's commonly used in the field to test VRLA batteries. So for the Albert cell corder, it uses DC current, and then it uses Ohm's law to calculate the internal resistance of the battery. And when we say the internal resistance, that is the resistance of the battery between the positive post and the negative post through all of the cells in that jar. Okay. So what the cell corder does is it actually has a bank of resistors inside the cell corder and a contactor or a relay. And when you press the button, it actually puts a load on that one cell that you are testing, or that one block that you are testing. And that load is usually between 50 and 70 amps. And you can see on the screen here, this is from the Albert cell corder manual. this is what it does. So at this point here, that is when the test starts, okay? And it applies the current to start off with. And what they're looking for is they're looking for where this line here starts to go flat. So when they see that this line here is going flat, that means the battery is at a steady state, okay? And then at this point here, the load is removed from the cell coulter. But the interesting thing that the cell coulter does is it's only looking at this very small area here, and that is an expanded view of that area. And what they're doing is they're using Ohm's law. So V is equal to IR, and then therefore R, the internal resistance of the battery. What they're looking for is the delta, or the change in voltage with respect to current. So basically R is equal to V over I. Okay, and they're looking for this line here, and that is the change in voltage. So as soon as the load is taken off at this point here, they're measuring the difference between V1 and V2. Okay, and you can see up here that V1 is 2.061 volts and V2 is 2.088 volts. Okay, and what they've done is they know the difference between that is 0.027. So they put 0.027 on the top there, and then they divide that by the current, which is 72 amps. And if you do the math, 0.027 divided by 72 amps is equal to 375 microohms. So that is how they work out the internal resistance of a valve regulated battery. And it must be noted that the higher the resistance over time, then therefore the less capacity the battery will have. So when we're measuring internal resistance, as the resistance goes up, that means the capacity of the battery is going down. So that is how the Albert cell coulter does it. Okay, and here's a battery that we have in our lab in Houston, and this is how you should set up your cell coulter for testing. So obviously we're testing this battery right here. Okay, and here is the positive post. So we put our red clamp on the positive post. On the negative post, we put the red and black clamp. And it should always be remembered that the red and black clamp is always going to be in the middle, because at the end of the test, we have this black solid clamp, which goes on the next battery's positive post. Okay. So what's happening in this picture here, when you press the test button, the current or the load is being applied between this terminal here and this terminal here. Okay, so that 70 amps current is going to flow all the way between those two probes. And the reason why we have this red and black probe, is this probe and this probe are measuring internal resistance. Okay, and then this probe and this probe are measuring the intercell resistance. It's like a micro emitter. Basically, they're using Ohm's law. They know, as we said in the slide before, there's about 70 amps flowing through there. And they know what the voltage drop is going to be between this point, and therefore using Ohm's law, they calculate what the resistance of the intercell connection is. So that is what the cell coulter is doing. Okay. For the other types of tests is the AC test. This top paragraph is taken from the Midtronics manual. But basically it says, instead of a DC load, the instrument injects an AC signal into the battery. So it's not putting a load on the battery, it's actually injecting an AC signal into the battery. And for the Medtronics, the frequency of that signal is between 80 to 100 hertz. And that's because at that frequency, the inductive and capacitive reactance meet together, they converge, resulting in a minimal voltage lag. And the difference between the AC test and the DC test is, for the AC test for the Medtronics, they are measuring MOS or Siemens or conductance, okay? And the lower the conductance over time, in other words, the lower the battery has the ability to conduct, then the less capacity the battery will have. So it's the inverse of the DC load test. So remember, for the DC load test, the higher the resistance, the less capacity we have. But for conductance, the lower the conductance, the less capacity the battery will have over time. And just to confuse things, the AC load testers don't have a standard. So for example, that bottom line there says the Fluke BT510 uses AC injection at around 1 kilohertz, and it measures resistance, not conductance. So the Fluke BT510 is injecting a signal into the battery, an AC signal, but the calculation they do is the internal resistance. So as the internal resistance goes up, the capacity of the battery will go down. So yes, it is confusing, but if you have any doubts, read the manual of the test device that you have, and it should explain it in more detail what it is doing. Okay. So that's how the testers test the battery. But what do we do with the values? What are we looking for? And, you know, we all love pass or fail tests. They're the easiest ones to analyze. But only a true capacity test following IEEE standards can do that. That is the only way you can pass or fail a battery, okay? The readings taken by a portable tester, they're only indicative of a problem. They're not telling you that there absolutely is a problem. It's indicating that there may be a problem, okay? And we need to have baseline readings to be able to analyze what's going on with these readings. And there are a few trusted ways to do this. And what I mean by a baseline reading is a reading that you can refer to and compare the measurement that you have just taken. And if it increases for resistance, then you know there's a problem. Or if it decreases for conductance, you know that there is a problem. So the few trusted ways to get a baseline, the best way is when you newly install the battery. They're saying that you should sample 20 or more of the new batteries and calculate an average of the baseline readings for that. Now, it's extremely important when you install that battery that you're thinking ahead and you know which portable tester is going to be tested and used on that battery over its life. So if you haven't bought one yet, then you have to make a decision. Are you going to use a DC tester like the cell caller, or are you going to use an AC injection tool like the Medtronics or the Fluke BT510? So once you make that decision, then you test 20 or more of the batteries, average all of the readings together, and then that gives you a baseline number that you will compare every test that you do from that point on to. Okay. The second way to get a baseline is to perform a capacity test, an IEEE capacity test, and then get the internal resistance baseline from a cell that passed at 100%. Okay. So you do the test. What you should do before you do the test is you should do your readings using your portable tester. And then when you get the results back, you find one of the batteries that had 100%, and then you look at your readings on your portable tester to see what the value of the internal resistance is on that cell or block, and that will be your baseline. The third way to do it is use a reference provided by the manufacturer. Now, that's not the best way to do it because you don't know what tester the battery manufacturer is using. You don't know how they are getting that information. And there is always going to be discrepancies between different manufacturers of testers, and even between the same tester from the same manufacturer, there's still going to be some discrepancies between two devices. So it's much better that you're using the actual device that you are going to be using to create that baseline. I hope that makes sense. So that is the way that we need, and then it's extremely important to get that baseline, because the readings mean nothing if you don't have something to compare them to. Okay. And here's an example of a C&D battery. This is for a UPS 12100, and the manufacturer is telling us that the internal resistance of that battery, they used a 60 hertz AC injection method, is 6,000 microohms or 6 milliohms. Okay. So that is an example of a battery manufacturer telling you what the baseline should be for that particular model of battery. So portable tester reading values can only be used to see trends. You know, it's if you haven't got a baseline and you measure a battery, you have no idea what you're looking for. So when you start to use a tester and compare it to a baseline, you have to see the battery trending higher for resistance or lower for conductance month over month. Then that is indicative that the battery is starting to have a problem. Now, the IEEE standard for valve regulated batteries is 1188, and that states that when a cell or unit internal ohmic value or internal resistance deviates by a significant amount from either the installation value or from the average of all connected cells units, additional actions are required. And that deviation is left up to interpretation. There is no industry standard, official standard, but the manufacturer of the tester will offer guidance. And it's usually, they say, 125% of baseline means that you need to look into things further, perform a capacity test maybe, and 150% maybe, okay, you need to replace the jar. But once again, it is left to interpretation. There is no official industry standard. It's up to you. It's up to how much money you have in the budget. Do you want to do a capacity test? There's so many variables in that nobody can create a standard. So what do you do if the deviations seem excessive based on all the information that you have at hand? Once again, IEEE 1188 is a little ambiguous on this. You know, it says that the reading should be trended over time and that the user should note any significant changes from the baseline. And depending on the degree of that change, either a performance test, cell replacement, or some other corrective action may be necessary. You know, they're not pinning themselves down to something, unfortunately. So the bottom line is that if you see that a battery is definitely trending in the wrong direction and it's starting and you can see it getting excessive, the bottom line is you must either replace that cell or perform a capacity test to prove the capacity of that cell. That is really the only two things that you can do. And it may be much more cost effective to just replace a cell rather than do a capacity test and then replace the cell. But once again, that is up to the end user to decide which is the best way to go. So that's internal resistance that we've been talking about. That's the actual internal resistance of the battery. That's looking inside the battery and trying to see if there's any plate degradation. Okay, because that is why the internal resistance or the the internal resistance goes up or the conductance goes down, is because the plates are starting to sulfate and break down. Okay. The other thing that most devices do, especially the cell coder, is they test the intercell resistance. And when we say the intercell resistance, that is the resistance of this connection to this connection. Bear in mind, I am not talking about the resistance of this cable, okay? It's not just the resistance of the cable. We'll get into this in just a moment. It's the resistance of the connection of that cable to the battery itself. And I'll explain that in just a moment, but it is extremely important to understand. So the test probes for the intercell connection must be on the post itself. So you can see here, we're going to zoom in, but you can see the jaws of these clamps are on the lead, the tin coated lead, or actually this, I think this is actually lead post, directly onto the lead post. They're not connected to the lug or the cable in any way, shape or form. Okay. And if we zoom in even closer, you can see the probe is only touching the post. It's not touching this lug part here, because if this connection on the probe touches this lug, then the test is void. It means nothing. All you're measuring is the resistance of the cable. That's not what we're trying to ascertain when we are doing the intercell resistance. We want to know what the resistance of the connection is. So from this post, we want to know what the resistance of this actual connection point here between the post and the lug. Because if this nut was loose, then this would have a higher resistance connection. If there was corrosion between the post itself and this lug here, and there was a layer, a barrier layer that was had higher resistance, that would cause a higher resistance connection. And it's critical that we keep our intercell connections resistance as low as possible, because when that battery is put in demand and has to supply current, then the resistance of these connections can add up and cause a huge amount of issues, which we'll go on to discuss in just a moment. And here's another example of a valve regulated lead acid battery. It's one of the stackable versions. Remember, if these probes touched this connection here, then the test is void. There's no point in actually doing the test, none whatsoever. So what you have to make sure is you get the correct probes for your device. And you can see here that the probe is only touching the post. It is not touching the strap connection. Okay. So therefore, we will be measuring from the post through the connection all the way through to the other side. I didn't show the other probe on here, but it would be connected on that post there. And then it would measure the connection between the strap and the post on the other side. So that is why it is critically important when either your plant staff or you yourself as a battery tester is going out to do the test, you have to ensure that the probes do not touch the intercell connector, or the test is void. The test is only measuring the resistance of the strap, and the strap is the strap. It's not going to degrade. It shouldn't degrade anyway. Where we want to measure the connection between the battery to the strap and then back to the battery again. I hope that makes sense. And here's why. This is kind of a complicated table, so hopefully I can explain what's going on. So this is a capacity test being performed on a battery, okay? And they're taking out about 500 amps, okay? Now, when you do a test on a battery, it is a constant power test that we're doing, okay? So in this example here, and sorry, this second one is volts, the voltage of the battery as the capacity test goes through its 15-minute period, okay? So you can see here at the very start, 498 amps times 324 volts. That means we are taking 16.1 kilowatts out of the battery, okay? Now we have to for this test to be accurate, we have to maintain 16.1 kilowatts out of the battery at all times. So you can see here at the very end, at the 15-minute mark, our voltage as the battery discharges has gone down to 303 volts. That means the current has to go up. But if you multiply 533 by 303, you get 16.1 kilowatts. So hopefully that explains what's going on in these two columns here. This is voltage, that's current, and they should both multiply together to give you 16.1 kilowatts. Now, what these following columns are is what the voltage would be if the average resistance of the connections, the intercell connections in microohms increased in microohms, okay? So what they're saying is if the the intercell connections on the battery only increased by 25 microohms, which is a very, very small amount, then the voltage dropped across those that higher resistance will mean we will get to our end voltage of 303 volts quicker at the 13-minute mark. So we're not going to get as much capacity out of the battery. Okay. Now, many people will say, well, 15 to 13 minutes, that's not excessive. But what you will see is as you go along here, when you increase the connection, the average connection resistance by 200 microohms, you're seeing as soon as you start the test, the voltage of the battery is going to go down to 303 volts, which is its end voltage, and therefore the battery has no capacity. It's going to seem like it has no capacity because all the voltage is going to be dropped across those resistors, and all the power is going to be dropped across those resistors. It's kind of difficult to understand from the table. So what I've done is I created this diagram, hopefully that will show you a little bit better. So in this one here, we've got 1, 2, 3, 4 batteries connected in series. And these resistances here are symbolizing the intercell connection resistance between one battery's negative post to one battery's positive post. Okay. And then we have our load bank connected here, which is going to be discharging the batteries at that 500 amp level that we mentioned in the last slide. So if the resistance of the connection was 200 microohms, that's going to drop an additional 0.1 volts across each of those connectors. And in that previous battery, there was approximately 160 cells. So that means across the whole battery, 16 volts is going to be dropped across those connectors. But more importantly, 8 kilowatts of power is going to be dissipated across those resistances. Those connections are going to start to heat up and dissipate power. Okay. Some people will say, well, 16 volts isn't a huge amount. 8 kilowatts, it's not a huge amount in the grand scheme of things. Well, look what happens when we move to 400 ohms. We double the intercell resistance. Now we're dropping 0.2 volts and 100 watts per cell. Okay. And then if we go even further and the intercell connections are 10,000 microohms higher, maybe they haven't been torqued correctly, maybe it's in a very dirty environment and they're corrosive, then there's going to be 5 volts dropped across each intercell resistance. 2.5 kilowatts dropped across each resistance. That's a huge amount of power. That's going to cause these connections to heat up and even start to melt. So it's extremely critical to make sure that your intercell connections are torqued correctly, they're clean, corrosion free, to make sure that your battery is going to give you the capacity you need, and that these intercell connections aren't going to heat up. Because I've seen many pictures that have been, batteries have started to explode or melt because these intercell connections heat up so much, and they can ignite the hydrogen inside the battery. Obviously not so much for valve regulated cells, but for wet cells. So it's extremely critical that you make sure the intercell connection resistances are measured correctly by making sure your probe is on the post and the following post, and that everything is tight and looks good. Once again, there is no industry standard for what to expect. Every resistance is going to be different depending on how big the strap connection is, how, its surface area, how long it is. Many things affect it. So once again, to get a baseline, you would have to make sure that the battery is installed correctly, and then get the average reading from all of those connections to get you a good baseline. So that's using the test tools and what they're doing. So the two things it's measuring is internal resistance, which is the internal resistance of the battery itself, and then the intercell resistance, which is the connection resistance between one battery to the next battery, or one cell to the next cell. So the frequency of testing via VRLA batteries, we go to IEEE 1188. Now remember, IEEE is only industry best practice. It's only a recommendation. It is not the law. Okay, so it is a standard, but it is not the law. And the frequency of the IEEE recommendations for valve regulated batteries are as follows: monthly, quarterly, and annually. That is what IEEE recommend for portable testing. Okay. Now, for monthly inspections, they're saying that you should use a calibrated and properly rated meter and measure and record the DC float voltage of the battery terminals. Okay. And also record the float current for each string. Now, the float voltage has to be within the range allowed by the manufacturer. Okay. Each manufacturer has different specifications for the float voltage depending on temperature. So, a lot of people say that it should be 2.25 volts per cell for a lead acid battery. And that's not correct. As a rule of thumb, yes, it is kind of correct. But some manufacturers will say 2.23 volts per cell. Some manufacturers will say 2.27 volts per cell. And if you don't charge your batteries at the correct voltage, then for valve regulated batteries, if they're overcharged, you're reducing the life of your battery. And if you undercharge any battery, then you are allowing sulfation to start, and you will lose capacity in that battery. So you have to follow the manufacturer's guidelines for what the battery should be float charged at. You should also measure and record the battery charger output current and the voltage readings at the charger output. That's what IEEE recommend. And that monitors changes in the load profile and can detect issues in connections and cables between the charger and the battery. Because remember, in many circumstances, the charger is not going to be in the same room as the battery. So it could well be that there is a battery disconnect, an external battery disconnect between the charger and the battery. And if somebody accidentally left that open, or if the contacts in that battery disconnect aren't working very well, you could, in theory, measure 135 volts at the output of the charger. But when you get to the battery, you could measure maybe 125 volts because there is a high resistance connection inside the external battery disconnect. So that's why it's important to measure actually at the battery terminals, the voltage, and at the charger itself, so you can see if there's any major difference. Okay, now there are going to be some differences in some circumstances because of cable drop, voltage drop in the cable if it's a long run. But when the batteries are being float charged, there isn't a huge amount of current flowing, so there shouldn't be a huge amount of voltage drop in those cables. Also, during a monthly inspection, you should visually inspect all the cells or units for evidence of corrosion at the terminals on the intercell connectors, and look at the case seals and pressure relief valves and make sure they're clear of debris, there's nothing covering them, and that the relief valves have the ability to allow gas to expel if necessary. Okay, if there is corrosion, that indicates that there is a post seal leaking. Okay, and in a valve regulated battery, a valve regulated lead acid battery, if there's a post leaking, that means pretty much the battery is going to die eventually, because what that allows to happen is the electrolyte, the water inside the electrolyte is getting is escaping from the cell because through that post seal leak, because it's not going through the recombination process. Those valves on a VRLA are recombining the water back into the battery. So if there is a post leak, that means that water is getting out of the battery and it will eventually dry out. Okay, which is no bueno for, that's how valve regulated batteries die. Because the electrolyte dries out and the plates corrode. Okay. Also visually inspect the cell unit cover for integrity and cracks. Obviously see above. If you have any cracks in the plastic around the battery, then that means electrolyte can leak out. Visually inspect the cell for excessive jar or cover distortion. Bulging cells are a telltale sign that that battery is going to fail, and it's going to fail very, very soon if it hasn't done so already. It means for some reason the gas inside that battery is excessive. That means it's probably been overcharged and it's going into thermal runaway, and it is not a good sign. They should be square in nature. They should not look like a football, for sure. You should measure and record the ambient temperature, okay, of the room, and that temperature should be 77 degrees Fahrenheit. If not, then the charger voltage should be compensated for temperature. So if the temperature goes up, then you should compensate the charger voltage down, and vice versa. If the temperature is cooler than 77 degrees Fahrenheit, then you have to increase the voltage of the charger. Also, during a monthly inspection, you should check for any unintentional battery grounds. An unintentional ground causes safety issues. Okay, basically your battery is in most cases supposed to be floating. In other words, it has no reference to ground. Now, let me caveat that. I know there's a lot of people that are going to shout at the screen and say, well, the voltage between my positive posting ground and my negative posting ground is halfway between the battery voltage. That is created artificially by a ground fault detection system in your charger. Okay, if you didn't have a ground fault detection system in your charger, you should have no reference between the positive posting ground and the negative posting ground. Okay, and what that does is it allows people to work on the battery safely, because obviously they're leaning across the rack is made of metal. Yes, it's usually covered in a plastic epoxy resin of some sort and is insulated, but there are going to be some breaks in that insulation. So if somebody is leaning across a battery rack and his arm or her arm touches metal on the rack and then touches a battery post, you should not be exposed to a shock. So if it's floating, you will not be exposed to a shock. But if there is a ground on the battery, whether it's accidental, it should be accidental, then that poses hazards for people working on the battery and could allow them to get a shock. And also it means, like, let's say there is a negative ground on the battery. It's not going to affect the operation of the system, okay? But if a positive ground comes along after you have a negative ground, then you have a direct short, and that will cause huge issues. That's why we check for unintentional grounds. And then during the monthly inspection, you want to clean all the battery surfaces of any foreign material. You want to check the battery room for proper ventilation, HVAC and lighting. Ensure there are unobstructed egress paths around the battery. Check for eye wash, spill containment if necessary. Obviously, for a valve regulated battery, a spill containment may not be required, and record any abnormalities. And then verify that the battery monitoring systems are operational if they are installed. So that's the expectations for a monthly inspection. For the quarterly inspection, well, they want you to do everything that you just did on the monthly, and then measure and record all cell unit voltages. And that is, once again, you have to check the battery manufacturer guidelines for expected spread voltage. And that's usually between plus or minus 10%. So once again, you can see on the screen here, this box here. Oh, goodness me, my circle is terrible. But that box there is actually from a C&D battery. I think it was the same battery that we looked at before that had the baseline resistance in it. And it says for float charge voltage, it should be at 13.65 volts. So this is a 6-cell jar, and the spread should be plus or minus 1.5 volts DC. That means you can go down to 12.5 volts and it still be within an acceptable range, or you can go up to 15.2 volts. Okay, so it's my math's terrible. It's a 3-volt spread basically, so that must be 15.5, something like that. So if the voltages of all the monoblocks are between that range, then you don't have to do anything. Everything is okay. It's only when they go out of that range that then you have to do something, and that is consult with the battery manufacturer's guidelines, and they may recommend that you do an equalized charge, and you have to follow the parameters that the battery manufacturer stipulates. You also have to measure and record cell unit internal ohmic values, and then trend those results and compare to the baseline data, as we mentioned before. There's no point in just taking those values and not doing anything with them. You have to trend them to previous results. And then measure and record the temperature of the negative terminal of each cell or jar, okay? And that is a good indication of the internal battery temperature. And then you have to compare that to previous readings. What do you do with that reading? Well, if the readings are starting to go high, but the room temperature remains the same, that could be an indication that your battery is starting to go into thermal runaway, which is disastrous. If your whole battery goes into thermal runaway, that can cause a fire. So that's why you have to pay attention to these readings and do them correctly, so you can see something that could happen in the future. And then for annual inspections, you augment the monthly, the quarterly, and then measure and record cell-to-cell and terminal connection resistance. And then it says here, if the resistance value is more than 20% above the baseline value or the string average, the connection should be disassembled, cleaned, reconnected, retorqued, and retested. As we discussed previously, that's the intercell connection. And then measure and record the AC ripple current and or voltage imposed on the battery. Now that's coming from either the battery charger or the UPS. And if nothing has changed within the system and the AC ripple current goes up, then that probably means that the filter circuit in the charger may be failing. The capacitors may be coming to their end of life. So once again, that's why we take these readings. There's no point in taking the reading and just writing it down. We want to know what's going on. And if the ripple current goes down, then the battery internal resistance may be increasing, which is indicating a loss of capacity. So all these readings do tell us something. That's why we take them. It's not just a case of it fulfills a work order. It actually does tell us something. Okay. And the last thing we're going to discuss is current limit. It's a very, very misunderstood concept. Okay. Current limit was designed to protect battery chargers. The only reason current limit was designed for chargers was to protect the semiconductors in the charger rectifier bridge. And what I mean by that is the semiconductors of choice in most chargers are called SCRs, silicon controlled rectifiers. So let's say we had a battery charger and the spec for that charger called out an SCR that was rated at 200 amps. Then the charger manufacturer is going to err on the side of caution and probably limit the current through those SCRs to approximately 100 amps, maybe 150, depending on the manufacturer. Okay, they don't want to exceed the rating of the SCRs because they may blow up or get damaged. So that is the reason we have originally why current limit was created, because we can create a 50 amp charger, a 100 amp charger, 200 amp charger, a 500 amp charger that use the same control boards and everything, and all we do is change the SCRs and the transformers to rate them up or rate them down. Now remember, Ohm's law never changes. V is equal to IR, or I, the current, is equal to the voltage divided by the resistance, and it never changes. Don't try and invent a new Ohm's law because it's not going to work. It's been proven over and over again. So let's say we have a 100 volt charger. I like 100 volts because it's easy to work with. And then we have a resistive load on the output here. Well, the full 100 volts is going to be dropped across that resistor. Quite simple. So we'll be able to find out what the current is if we know the resistance of the load. So if our load was 1 ohm and our charger is putting out 100 volts, I is equal to V divided by R, 100 divided by 1. That means for a 1 ohm load connected to this charger here, we are going to have 100 amps out. Hopefully everybody understands that. Relatively simple. But we don't have any control on that load, okay? Let's say somebody added additional load onto this charger, didn't ask for permission, added twice the load. That would cause the resistance to drop by half because it's inversely proportional, okay? So that means that now our load has gone down to 0.5 ohms. If our charger is still putting out 100 volts, Ohm's law says, okay, now we have 200 amps coming out of that charger. Once again, no bueno. That's not good. The SCRs inside this charger could fail because of that high current. So it's important to remember, we cannot directly change the current. We have no control over the actual current from the charger. The only thing that we can control in the charger is V. Now remember, we can't control R because that's the plant load. Whatever the plant load is whatever the plant load is. And we can't change the I. Okay, the only thing we can change at the charger is V. Okay, and that is how current limit works. It's actually changing the voltage to keep the current at what we want it to be. So in this situation here, to get this current of 200 amps down to 100 amps, which is the safe rating of that charger, what it would have to do is it would reduce the voltage of the charger down to 50 volts. Once again, if you use Ohm's law, 50 volts divided by this new load of 0.5 ohms, we're back down at 100 amps. Safe. The SCRs are not going to blow up and everything is good. That is how current limit in nearly all chargers works. We are not changing the current, we are changing the voltage, which will then change the current dependent on the resistance of the load circuits. And this last drawing here is from an AMETEK SCI UPS. And on our modern DPP UPSs, we actually now have two current limit. We have a current limit here, so that's actually current limit for the overall DC of the system, and then this shunt is measuring the current to the battery. So we have two on our DPP UPSs. We have a two-stage current limit. We have an overall charger output current limit, and then a battery current limit. Okay. The battery current limit is dependent on what the battery manufacturer tells us. And this is a contentious issue, in my opinion. You know, if you designed your battery, like this battery here, for example, this is a C&D battery, okay? And it's saying here, this is constant power. So for 5 minutes at 12 volts, it's saying that you can get 1058 watts. Okay, so let's say that's 10 volts just for ease. You would divide 1058 by 10, that would give you 105 amps. So this table here is saying this battery is quite easily going to give you 105 amps without any issues. Okay, but what C&D are saying is the recommended maximum charging current limit should be C5 of the 20-hour rate. C divided by 5, okay? So in other words, what they're saying is the 20-hour rate for this battery is 206 amps. So they're saying that you should limit the current to this battery to around about 41.5 amps. To me, that doesn't make sense. Now, the battery manufacturers may have a good reason, but if the battery can supply 100 amps, why on earth can't the battery accept 100 amps in charge? I think what they're trying to do is make sure that the charging process doesn't overheat the battery, which can cause thermal issues inside the battery, which can cause thermal runaway eventually. That's what they're probably trying to do. For wet cell batteries, I have no idea why they have limitations on the battery. But that is why we now have two-stage current limit, because most of the battery manufacturers are now telling us that the current to the battery should be limited to a certain value. Okay, goodness me, I spoke too much again. That's nearly an hour. Let's go to the questions. And let's see what we have. Thanks for listening, everybody, and for watching. So could you please share your, actually the first one, if a new battery bank is not as good as it was stored for a long time and we take the average conductance, we might take an incorrect baseline. That is actually very true. So you have to follow the manufacturer's guidelines for a battery that has been stored. You know, sometimes it's out with our control, but the battery manufacturer will tell you that if you're storing, if you buy batteries, it needs to be stored correctly. And they'll give you maybe 3 to 6 months of not having to charge those batteries if they are stored at 77 degrees Fahrenheit. If you don't follow those recommendations, then all bets are off. And you would probably have to do recharge those batteries, do a capacity test, and do the find a battery that passed at 100% to get the baseline value that way. So the next question is, can you share your opinion for the following example? A battery bank with 60 cells has 10%. What is the deviation value that we should take some additional actions? It's such a very ambiguous question because there are so many variables involved. I don't know if I can. I'm more of a UPS guy. I'm not, I used to work on batteries a lot, not as much as I used to now. The cell coder will give you recommendations, the Medtronics will give you recommendations, and all the devices will give you recommendations on what they think that you should do. I'm not in a position where I'm going to pin myself down to a value. But what I would say is, if it's going up by 10% month over month or quarter over quarter, then that is indicative that the battery is going to fail soon, and I would replace that battery. When you see things constantly going up compared to any other battery in the string, that is definitely telling you something inside that battery is wrong. Okay, so Daniel's question, he cut it off. So a battery bank with 60 cells has about 10% of the cells that have 60 to 70% conductance given by the Medtronic. Although the rest of the battery cells are above 90%, the UPS fails to run on battery load. Is it advisable to replace the entire bank? Ooh, that's a very good question. I think most people will say you would need to see at least 20% of the battery fail before they would recommend the entire string is replaced. It's a difficult one because it's all down to cost. That's basically what it all boils down to, You've got to weigh up risk versus cost. And because the battery is connected to a critical load, I would go to the plant and I would say, hey, look, we've got indications that 10% of your battery is failing. The rest of the batteries seem to be okay, but it's indicative that some of those cells are starting to fail, which could lead to the other ones failing if they're from the same batch. Then it may be advisable to replace the whole string. It depends on how old they are, the temperature of the room. There's so many variables. I really wish I could give you a specific answer, Daniel, but there's just so many variables there. How do you measure AC ripple current? You get an amp clamp, and it has to be an AC or an AC DC amp clamp, and you turn your amp clamp to AC, and you put your amp clamp around the main positive or the main negative cable going to your battery, and then you take your reading that way. That is how you measure the AC ripple current. How can you determine the charge current for a bank? It's the same thing. You use an amp clamp. Now for DC, for the charge current, it should be a very small value in the milliamps. So you have to have a good resolution amp clamp, and you have to zero your DC current as well. DC current, your amp clamp should have a zero button, or it should have a dial that allows you to zero out the value before you put the amp clamp on the cable. But you want to measure the small amount of current that is going to the battery, DC current. So ripple current is AC, charge current is DC. Colin, I think about this all the time. He's asked, why can't VRLA jars be translucent material? I think because it would look ugly, and you wouldn't see much, because the plates are there are glass mats, or there is a gel material inside as the electrolyte. So you're really not going to be able to see the plates and get any information if they were translucent, and they would look very ugly. But I think it's a good question. I think if they could figure that out, it would give us an additional thing to look at. Could I repeat the maximum battery charging limit? That is dependent on the battery manufacturer. You have to get that from the battery manufacturer's data sheet. For that C&D battery, it was the C rating of the battery divided by 5 at the 20-hour rate. So the 20-hour rate, so that's 206 divided by 5, which would be 41.5 amps for this specific battery, which is a UPS 12700 MRF. Does not apply to any other battery, only this specific model and manufacturer. Okay. Logan asks, can we email the slides? Nope, unfortunately the slides are proprietary, but you can share the video to whoever you want. We do not email slides. I know you're intimately familiar with the cell coder. Do I have any experience or thoughts on the Fluke BT520 method of testing? I don't. I haven't used one, Aaron. I would assume, because Fluke is such a reputable company, that they have done their homework and they saw a gap in the market where the BT520 or 520, whatever you want to call it, fills that gap. I would suggest that if it's on the market, then it does a relatively good job of testing the internal resistance. In truth, technology has come on leaps and bounds since the cell coder was invented, and it's still using Ohm's law. They're injecting a signal, measuring the voltage drop, and then calculating the resistance and from the current that they see. It's, in this day and age, it's not rocket science. The problem that I have with any tool that injects current into a battery that is connected to a UPS is the UPS will reflect frequencies back onto the battery. So, like, for example, our ferroresonant UPSs, we switch the inverter at 60 hertz. So therefore, there is going to be a 60 hertz reflection back onto the battery. And therefore, if the Medtronics is sending a signal between 50 and 100 hertz to that battery to monitor what's going on, then I think our ferroresonant UPS is going to affect that value. Now, I think for the Fluke BT820 or whatever, 520, sorry, it's injecting it at 1 kilohertz. Our DPP UPS's switching frequency is 8 kilohertz, so that shouldn't really affect it. But, there are going to be some instances where it might. So whenever you are injecting a very small voltage signal into a battery, you are going to be open to some false readings because of noise created by the inverter or noise created in the environment, in my opinion. That's why I prefer the cell coder, because it's actually definitive, that it's taking a load out of the battery and then measuring that very small recovery period. The UPS interaction, the inverter switching, is not going to affect the cell coder. But if anybody has had good experiences with the BT520, let us know. What is the ideal method for sizing the battery bank? Okay, Mashak, I have a presentation on our YouTube channel that goes over that. For a UPS, it would be the constant power method. For switchgear systems, it may be better to do the constant current method. But there is a presentation in our YouTube library that does go over how to size a battery for a UPS. Another question, can we install for a temporary time batteries in parallel with the same voltage but different ampere hour? Absolutely, yes, you can. But you will, obviously, if you temporarily put a battery in parallel that has less of an ampere hour capacity, those batteries are going to get to their end of discharge quicker, and then you will be back to just having one battery, if you know what I mean. But yes, you can do it. It's not recommended, but you absolutely can do it without any issues. What's the minimum recommended conductance to consider when testing batteries with battery analyzer? I cannot answer that, Denise, because it is all battery specific. The bigger the battery, the more substantial the plates are, whether the plates are made of lead or whatever. It's of pure lead. All affects how that battery, how its conductance or resistance is. So there is no true answer to the minimum recommended conductance, unfortunately. What is the effect of connecting series new batteries with old batteries that are still more or less healthy? There is, as long as the new batteries are charged as per the manufacturer's guidelines before they are put into the string, then there should be no problems. Obviously, you don't want to introduce a whole load of new batteries into a string that has old batteries, because those old batteries are eventually going to fail as well. But there is no effect as long as you make sure that the new batteries have been charged up correctly. Because if they're not charged up correctly, then they will want more current to get charged up, and that will draw current through the other batteries that don't need that current, and will cause an imbalance in voltage across the string. How can you adjust the battery current limit on an AMETEK UPS system, or do you need an AMETEK specialist? That's a very good question. I don't think, in fact, I'm pretty sure you need, the current limit is set at the factory, and you would need an AMETEK specialist to adjust the current limit. That is all of the questions, and goodness me, look at that. It's 10 after 12. I really need to get better at keeping this to an hour. Thanks, everybody, for watching this presentation. Thank you for all the amazing questions. That's excellent. I always love to see lots of questions at the end of a presentation, and I hope I answered them all as best as I could. If you would like to get in contact with us, if you have any questions or concerns, you can go to our website, AMETEK Solidstate Controls. The link is going to be posted in the chat. The recording of the presentation will be on our YouTube channel. That is posted in the chat. And if you have any questions, concerns, just go to our website, press the contact us button, and that will be disseminated within the company and put to the right person. So once again, thank you for putting up with me for an hour and 15 minutes. I hope that you enjoyed this presentation and it had some good information. It's a pleasure, as always, and there's London. She's put in the link to the website. Look out for the survey that's going to go out. Once again, one of the questions is, what topics do you want us to go over on the next webinar? I do read every one of those, so I'm always looking for good ideas, and that's why we went over current limit today, because somebody mentioned in one of the surveys that they wanted us to go over current limit. So please keep on letting us know what you want us to discuss. So until next time, thank you very much indeed. Take care, and I look forward to speaking to you next month. Thanks very much, everyone.